Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is yet another video on polar coordinate system. If you have not watched them, then you should probably watch my videos on the derivation of the polar coordinate system, converting ordered pairs between polar and rectangular coordinates. In this video and the next, we'll work with converting equations. And this is something that's completely weird to people, but there are equations in polar coordinates. So they are, remember, polar coordinates are coordinates of the form r comma theta. So just like in the Cartesian coordinate system, we have points x comma y. So therefore we have equations relating x and y. So you have stuff with y's equaling stuff with x's. They can be mixed all over the place. Well, the same thing happens with polars. You will have equations involving r's and thetas. So r's on one side, thetas on the other, or they might be mixed together, something like this, right? So those would be polar equations. And just like you learned way back when in your elementary algebra or pre-algebra courses, you start working with equations first. You start saying like, okay, well, what if we had y equals 3x plus 1? Let's build a table of values. Let's do this, that, and the other. You didn't start graphing until you dealt with building tables and doing stuff like that for a little while. But then after that, you did start graphing. We're going to do the same thing here. We're not going to build tables of values, honestly, but we're going to play with equations a little bit. And then eventually, not in this video, but in the next, in a few videos from now, we'll start graphing these. The graphs are very beautiful, so they're really fun to deal with. But for now, let's go ahead and convert this equation into rectangular form. All right, looking at this equation, it's very difficult to imagine how you would change this into rectangular form. One thing I need to state here is there's a little caveat with this specific, the very first equation here. So what I'm going to do is modify it slightly, and then we'll come back to this. So let's just pretend as though it's r equals 5. Not r equals negative 5, but r equals 5. We know we have some very special formulas when it comes to polars. Our formulas are these. X is equal to r times the cosine of theta. That's actually not going to help us here. Y is equal to r sine of theta. That's not going to help us here. R is equal to the square root of x squared plus y squared. That is going to help us here. And in fact, the way I'm going to write this is I'm going to square both sides. I'm going to say r squared is equal to x squared plus y squared. That is really going to help us here. And then finally, we do have this last bit here that the tangent of y over x, tangent of theta is equal to y over x. That's not really going to help at all, but these are the main formulas for polar coordinate work. I'm just going to box that up and copy it so that I have it and I can paste it into future problems. Let's go ahead and just see what we could do here. Using those formulas, I see r is equal to 5. Well, I know that r squared is equal to x squared plus y squared. Therefore, the square root of that, let me go ahead and point that out, r itself must be, now watch how I do this, plus or minus the square root of x squared plus y squared. Now, I know what you're going to say, but wait a second. In the previous video, you told me r is equal to the square root, not plus or minus, but just the regular old square root. What I said in that video is when you're converting from Cartesian coordinates to polar coordinates, there's an infinite number of representations. And in that conversion process, we just want to simplify it. So we're just going to restrict our radius to be the positive version of that. However, in reality, the radius could be negative. It could be one of the other representations. So just letting you know, r is equal to plus or minus the square root of x squared plus y squared. If you insert that here, you would get plus or minus the square root of x squared plus y squared is equal to 5. Now, the fact that 5 is positive really removes the negativity from that. So in this case, the square root of x squared plus y squared has to have a positive in front of it because we're dealing with a positive 5. Then you would square both sides and you'd see, oh, you know what this equation is? It's the equation of a circle of radius 5. Huh, cool. And in fact, you could quickly graph that, right? Here's my circle of radius 5 centered at the origin. Let's just pretend that's a radius of 5 circle. So that's what this equation is. This equation is the equation of a circle of radius 5. Very nice, clean equation. Now let's go ahead and rewind the tape and consider the initial question. The initial question was this: what is the rectangular form, or the Cartesian equation, for r equals negative 5? Well, you could start by just squaring both sides. R squared is equal to 25, and then you know r squared, from our blue formulas over to the left there, is equal to x squared plus y squared, and you get to the same exact formula. So it turns out the negativity on 5 doesn't actually matter, but it was just a kind of a hard conversation to start the problem with. Okay. So again, r equals negative 5, by the way, is a circle of radius 5 in the polar coordinate system because imagine, polar coordinate system. Imagine you start at the pole, you face the polar axis, and you say, all right, well, in this equation, what if I'm facing an angle of 0? What's r? Well, if you're facing an angle of 0, r is negative 5. Well, let me plot that. I'm facing an angle of 0, this direction right here, but I'm going to plot a point 5 units behind me. Let's just pretend that lands right here. Now you say, okay, I'm going to face an angle of pi over 2. What is r? Well, r is still negative 5. So again, you're facing the angle pi over 2. You're going to actually plot a point 5 units behind you. Right there. And then you say, well, what if I'm facing an angle of pi? What's r? Well, it's still negative 5. So if I'm facing this direction, which is pi, I'm going to plot a point 5 units behind me. Same thing if you're facing downward, you plot a point 5 units behind you. So really what you're plotting is a circle of radius 5. So it is the same circle, no matter what. What if instead you're dealing with this? Convert this to rectangular form. You have the equation in polar coordinates. Theta is always equal to pi over 6. Notice how I said that. Theta is always equal to pi over 6. None of these formulas really are going to help you. They kind of will, they kind of won't. Actually, there's one there that will help. But I'm going to go ahead and just say, let's build a table of values. Let's see what happens. So remember, we have r versus theta. Theta is always pi over 6. Always pi over 6. I mean, really, always a pi over 6. So no matter what your radius is, if your radius is 0, well, theta is pi over 6. If your radius is 1, pi over 6. If your radius is negative 1, it's pi over 6. If your radius is 2, it's pi over 6, right? No matter what, your angle is always pi over 6. So if I were to go plot the pole in the polar axis, and I were to say, okay, I'm going to plot this point. First, I'm going to turn through an angle of pi over 6, which is roughly that short little angle right there. And I'm going to step out 0 units. Then I'm going to face an angle of pi over 6 and step out 1 unit. Then I'm going to face an angle of pi over 6 and step back 1 unit. That's not exactly correct, but whatever. Then I'm going to face an angle of pi over 6 and step forward 2 units. If you could tell, it's plotting a line where the angle that line makes with the pole is pi over 6. And that's what this is. It's a line going through the pole with an angle of pi over 6 from the polar axis. Another way you could have done that, by the way, is to use the formula for the tangent, which is something I would rarely do, but you could totally use that here. You could say the tangent of pi over 6 is 1 over root 3. If you didn't remember that, that's one that I don't often remember. Pi over 6, pi over 3, 1, 2, root 3. The tangent's opposite over adjacent, so that's 1 over root 3. And so this just tells us the ratio of y to x is always 1 over root 3. The rise is 1 for the run of root 3. And so it is a line with slope 1 over root 3. It rises 1 for every root 3 it runs. And that's not actually the way I would like to do this problem, but that is true. That's how this works. But for the most part, if somebody hands you an equation, theta equals some number, it's just going to be a line through the pole, and the angle is going to be that number. So if it's a negative 5 pi over 4, then, well, you start by facing a negative 5 pi over 4, and then you just draw a line. Very, very nice. Now, those previous two examples are kind of the exception examples. Those are the examples that every polar equation problem starts with, because you just start looking at these r is equal to number or theta equals number. But in reality, most polar equations look like this. They're a mixture of trig functions and r's. What you're going to do is reference this list right here. So I know that r squared can be traded out for an x squared plus y squared. So I'm slowly going to convert. This r squared is an x squared plus y squared is equal to 4. Now, sine of 2 theta. I don't have a sine of 2 theta here. I have a sine of theta. So what I need to do is use an identity to trade that out. So I'm going to trade out the sine of the double angle for 2 times the sine of theta times the cosine of theta. Nobody told me to. I'm doing it because I have to. So far I have x squared plus y squared is equal to 8 times sine of theta times the cosine of theta. Notice I left a little space in there. The reason why I left spaces in there is because I don't have just a sine of theta and a cosine of theta. I have r sine of theta and r times the cosine of theta. A little trick in mathematics that you need to get used to is if you want something to happen. So if I want, for example, this sine to have an r in front of it, force that to happen by multiplying both sides by r. So I'm going to grab the left-hand side, and I'm going to multiply it by r, and I'm going to multiply the right-hand side by r. Well, now I could do kind of the same thing for that cosine. I'd love to multiply that cosine by r. So technically, I'm going to multiply the right-hand side by r squared. So I better multiply the left-hand side by 2 of those r's, or r squared. And when you do that, you get r squared times x squared plus y squared is equal to 8. And we know that r sine of theta is y, and r cosine of theta is x. Y times x. I dislike writing things not in alphabetical order, so let's go ahead and rewrite that in alphabetical order. Also, note r squared is x squared plus y squared. So that's going to be an x squared plus y squared times an x squared plus y squared, or in other words, x squared plus y squared squared is equal to 8xy. That is the rectangular form of this polar equation. Notice the polar equation is a lot simpler. And that is generally the case. Polar equations look cleaner for the most part. Specifically because polars work on like this rotational system, they are much cleaner when you're dealing with curves that are rotational like this. If you have a curve that has a lot of like rotations to it, then it's better represented in polar coordinates. So again, given a polar equation, the best thing to do is start forcing forms like this. So I had an r squared immediately, so I traded that out for an x squared plus y squared. I did not have a sine of theta. I had a sine of 2 theta, so I used an identity, trig identity. And then I noted, well, I would love to have an r in front of the sine and an r in front of the cosine. Well, then place them there, but just whatever you do to one side, you got to do to the other. Right? So there you go. That's a good tactic to follow. Yet another example. Again, this one is not the easiest to see what to do with. When I see something like this, I immediately think I need r's in front of those sines and cosines. So what I would do in this case is I would just grab this side and the other side, and I would multiply both denominators by r. So I'd multiply both sides by 1 over r. And that's because, well, it just would work nicer that way. I would be guaranteed to get an r cos and an r sine. On the left-hand side, you'll just get a beautiful number 1. On the right-hand side, you get 1 over, distributing that r, 4r cosine of theta, minus 3r sine of theta. You could do a little trick here if you want. I'm going to just do one other thing here. 1 equals 1 over 4. We know that r times the cosine of theta, forgot to paste that in here, but r times the cosine of theta, that is equal to x, and r times the sine of theta is equal to y. So r cos theta here, that's going to be x minus 3 times y. And I would probably take the reciprocal of both sides, honestly. If you take the reciprocal of both sides, reciprocal of 1 is 1. Reciprocal of the right-hand side is 4x minus 3y. And there you go. That's the equation. It's the equation of a line, actually. And I think what I'm going to do is at the end of this video, I'm going to showcase all of these polar equations in a graph, because I think that'd be really neat to see. The final equation we have in this video to convert is this guy right here. Let me paste in our work there. And this is kind of quick to see. R squared will become x squared plus y squared. But before I make that conversion, I want to change that cotangent out. There's something kind of interesting going on here. So this cotangent, because the conversion process to between Cartesians and polars requires cosines and sines, I'm going to change that cotangent out to a cosine of theta over a sine of theta. But then when you look at that, you also should note those don't have r's in front of them, but you can totally multiply the numerator and denominator by r because that's multiplying by 1. And now that I have that done, I can totally trade everything out. R squared is x squared plus y squared, and r cosine of x, or sorry, r cosine of theta is x, and r sine of theta is y. You could technically multiply both sides by y if you wanted to, but that's not really going to make this any better. But if you did, you'd get this, I suppose. And now I'm kind of excited to showcase what all of these look like, because you can see this equation right here is not something that you know what its graph looks like or anything, so it might be neat to see what this looks like in polar coordinates. So here we are, we're back to Desmos here. Actually not back, we're just using Desmos for the first time. If you didn't know, Desmos has the ability to plot out a polar coordinate system. That's just this part right here. You can turn on or off the axes number, so I just have them on in this case. You could also turn off the axes themselves, but I'm going to keep the x and y axes on there. And it also understands polar coordinate equation or polar equations. So for example, I have on right now r equals 5. If I decrease that or increase that, you could see it's just a circle of radius, whatever number that I'm dealing with. Now the first problem actually had r equals -5. So if I go to -5, you'll see it's actually just a circle of radius 5. So it shrunk down and then pops right back out. Another thing you may or may not know about Desmos is that you can animate this stuff, but I'm not going to. So I'm going to turn that equation off. Now I'm going to look at r squared is equal to the 4 sine of 2 theta. One thing that Desmos cannot do is it cannot graph r squared is equal to anything. So instead, I have to solve for r. R is either equal to plus or minus the square root. They're actually the same value. So here is that r squared is equal to 4 sine of 2 theta. It's a beautiful curve there. And if I were to graph the other one, the negative square root, it's the same value. So they're the same problem there. But anyhow, that's the beauty of working with polars, is that you can get these wonderful curves very easily. The equation that was r is equal to 1 over 4 cosine of theta minus 3 sine of theta. We said that was a line, and you could totally see it is. And let's see. Oh, by the way, I think in that problem specifically, when we solved it or put it in rectangular coordinates, we got 1 is equal to 4x minus 3y. And if you look, it is actually, if I turn off that line, you can see they're the same line. So turn on the Cartesian coordinate versus the polar, they're the same line, exactly the same line. So that's fairly comfortable knowing that we have done our job correctly. The last one was r squared is equal to the cotangent of theta, which gave us a weird rectangular equation. This is what it looks like. Very beautiful equation. And remember, the rectangular equation we got from that one was x squared plus y squared. So let me turn this off and I'll just type in here. X squared plus y squared is equal to x over y. And you can see that's the same exact graph. In fact, let me turn that on again. There you go. The same graphs. So polar coordinates are really beautiful to work with. They give you these wonderful swoopy-like curves. And there's a lot more that you can do with them. But for right now, we're going to stop this video. And in the next video, we are going to convert from rectangular form into polar form. Basically the opposite direction.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.